Okay, now it's the essence. Okay, so this is the essence of a double replacement reaction. We have two solutions. Silver nitrate, AgNO3, forms no salt. If you look on your solubility table, cross those two together and you'll find that it's white. Okay, NaCl, we've already shown that to be white as well. So we're taking two solutions, dumping them together. That means we have two more combinations that weren't available before. The new combination is AgCl and sodium nitrate, NaNO3. So now we need to check solubility on both those new combinations. So we go over here to our handy dandy chart. They come together, the silver and the chloride are black. That means it forms a solid. You don't know the color, it happens to be a white solid, but you don't know the color until you actually do the little test we're going to do in lab today. The other one, sodium, remember the whole column is white. So that means sodium doesn't form a solid with anything. Same with nitrate. Nitrate goes all the way across on a row, totally white. So it doesn't form a solid either. But the silver and chloride do. Back in the 1930s, a very common, in the 1930s, we had very few instruments in CSI labs or wet chemistry labs. And so we had a lot of wet chemistry kind of tests to do. One test for halogens, that means chlorides, bromines, and iodines, was we'd add silver nitrate. And if it turned white, we knew that a halogen was there. We didn't know which one though. We didn't know if it was chloride, bromide, or iodine, but we knew a halogen was there. It's a very sensitive test. It's a little pricey nowadays. The silver is real pricey right now because of the stock market craziness. Now we did that last week also using silver nitrate. We had a metal in an ionic solution there. So last week we talked about metal and a salt. Metal, that's the key, except for one exception, that was the acids, but everything else was a metal. Metal becoming oxidized or reduced. Okay, that's single replacement. Double replacement are two salts. There's one salt and then there's another salt, different. Okay, so there's no metal, no oxidation reduction going on. It's purely a crystal lattice force, solvating force battle with a double replacement. Okay, so over here, now sometimes you'll see the word precipitate. That's a fancy way of saying solid. So you're going to see a little s is a subscript and a PPT is a subscript. You're free to use either one. Usually we use PPT when we're talking about a double replacement reaction because we're actually forming a solid and that's called precipitate. But both solids. Also, you'll see, talk about this last week, AQ. AQ stands for aqueous. aqueous, aqueous. Forgot if there's an ear. Either. Anyway, aqueous, AQ means it's dissolved in solution. Dissolved, no solid involved. So from now on until the end of the semester, we need to put AQ on our stuff to make sure you know it's in solution, or SLG, solid, liquid, or gas. Sometimes it forms a liquid, sometimes it forms a gas. Okay, so all we're doing is in a double replacement, we're just swapping cations or swapping anions. And then that goes hand in hand with some kind of solubility rules or solubility chart. So you have to distinguish between what kind of reaction is it? Is this single replacement? Double replacement, in my opinion, next semester I'm switching the labs around. We're gonna do double first rather than single. I think double is easier, especially with this nice solubility table. It's just really straightforward to do. Now, we talked about last time, we talked about a spectator ion. So in this case, the sodium is a spectator ion. And so is the nitrate, spectator ions. They remain AQ because they didn't form solids. Silver chloride, we have to put either S or PPT under it because it formed a solid. So everything is going to be subscripted. Now there's one more little interesting tidbit about double replacement reaction is the net ionic reaction. That is if something happens. Okay, so for example, we had the silver ion and the chloride ion forming silver chloride. Notice I put the AQ on the left side because those are still in solution. So we have two cation and an anion in solution. When they come together, they form a solid, hence the S. So this is net ionic reaction. Net, that means something happens. And when I say net, so if a solid, liquid, or gas forms, you have a net ionic equation. Sometimes they say NIE. In fact, I think your dry lab says NIE. But the net part is your key. As soon as you see, if they want to know net, whatever, then something happened. And that's when you use your solubility table. Now, what about this LNG stuff? Sometimes you get a gas form. It'd be a G. Like last week we had, remember we had the gases in some of those reactions, we had gases formed, little bubbles formed. In that case, it's not going to be AQ, it's not going to be S, it's not going to be L, it's going to be G. And there's one that's kind of tricky that has no visible reaction, but it happens. And that is a bless you, a neutralization reaction. Now, this is going to sound silly, but we have to put an L here. You could also put an S or a G there, depending on the temperature. But of course, room temperature is going to be an L for liquid. Even though it's an aqueous environment, we're still producing a little more water. And that's reflected in the products over here on the right. Now, the problem is, at the scale we're doing this lab today, little bitty bits, you're not going to know. And there's one more thing here. Heat. You're not going to be able to know heat's formed because the quantities are too small. So you're going to have to know that if we have an acid and a base, and the acid frequently will be like HCl, the base is frequently sodium hydroxide or potassium hydroxide, that these guys are going to form water. And you're going to have those today in the lab. Okay, so that's basically double replacement reactions. I don't think they're that wildly complicated or anything, as long as you have a nice solubility chart or rules that you were forced to memorize. Not too bad. So in fact, for future generations, we're going to do this lab first. Okay, so any questions about double replacement? Okay, so in lab today, what I want you to do is predict first, based on our solubility table, based on the combination. Now, you're going to be doing this on a piece of, we're not going to use spot plates today. We're going to be just using this black, you know, in a notebook, when you want to separate stuff, frequently you'll have a page, you want to, it's like a sheet protector on top of the page. And that's what we're going to be doing the lab on today. It's that. No spot, so it's really quick. You go boom, 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 you predict first. Prediction, just like we did last week. Predict, yes, we're going to get a solid or a gas or liquid, whatever. Drop, drop, drop. Nope. Go on to the next one. Really quick. And it's colors and all kinds of cool stuff. Okay, so that's what I wanted to cover today. Give you an introduction to double replacement reactions and naming ionic compounds, and even a little bit on covalent compounds as well. So, are there any questions? Now, we're going to have lots of room today